Hello, my name is Vishal. In this part of the tutorial, I will guide you through a presentation of the Excel sheet that I use to estimate water balances. This example is from an 88 square kilometer watershed in South India. First, we enter the three parameters that I mentioned earlier. These are the available water holding capacity, which I've entered as 40% here. Next, you need to estimate the root depth in your study area. In my case, I've estimated it as 1 meter or 1000 mm. The model then calculates the available water content in mm by a simple multiplication. Next, you enter a value for the reservoir coefficient. In this case, I've entered 0.8, which means that I'm going to let 80% of the excess water in any one month become stream flow. You will see later on how these three parameters affect the response of the model. Next, where did my input data come from? I had monthly precipitation data or rainfall data from 3 rainfall stations, and I used a spatial average for each month based on Thiessen polygons. For the potential evapotranspiration, I have used the Priestley-Taylor estimates of potential evapotranspiration, which I generated and are up on the India Water portal. The water balance was conducted on a monthly time step since the data was available at a monthly time step, and I had about 6 years or 6.5 years of monthly data available. Now I'm going to scroll down to the data columns themselves so that I can try and describe them to you. As you can see, the first column here, the first two columns, these two, are just the timeline, starting in my case from Jan 1990 and goes down to 1996 May. As you can see, as I scroll down here, 1996 was the end of my data period. So the model inputs are just rainfall and potential evapotranspiration, which are these two columns. So these are the two columns that you need to enter. Now let's move over to the right here, and we have several columns where the model calculations are done. Out here we have the accumulated potential water loss, soil water, the change in soil water, actual evapotranspiration, deficit when actual ET is less than potential ET, surplus when the soil water exceeds soil's available water capacity. Now, as you can see here on the right, I also have a column. Let's move this over to the right a bit. I also have this column, which is the actual flow as measured by some government agency. And this is very useful to compare against the predictions of the model simulated stream flow. And finally on the right, I also have summed up the monthly values to get annual totals. Annual totals are useful to compare all the different model predictions like the simulated flow, the actual evapotranspiration, and then compare it with the annual rainfall. I'll show you a little later how to calculate drainage or just get a rough idea of the drainage or groundwater recharge from the model. So finally, I'm going to wrap this up by saying that in the next part of the tutorial, I'm going to show you the effect of these three parameters, the AWC, the reservoir coefficient, and the routing depth. Alright, so I showed you what the different columns of this spreadsheet were. And in terms of filling in the equations, there's the first part of this tutorial, the PowerPoint presentation video that you saw, that is material on the website, the India Water Portal, from which you should be able to fill in the equations inside the spreadsheet. So for example, by now you would have seen this spreadsheet with these equations earlier on the India Water Portal. And these equations are exactly what's filled in over here. For example, for accumulated potential water loss, the equations that you see out here are the same as these in this table. And when you download the sample spreadsheet, it will get clearer. So what I want to show you right now is what the output looks like. So you've run this model and it's done all these calculations. There are all these numbers, but what does it mean? Well, when you graph it, you get a sense of what it means. And I have graphed it. I'm just going to pull this graph to the left to show you what it's all about. Just a second. And in this graph, what we have on the x-axis is the timeline. Jan 90, May 90, September 90, every single month that we've modeled it. On the y-axis, there are three graphs. These bars on the top are the rainfall data. The black flowing line is the actual flow, and the blue is the simulated or the model predicted stream flow. So what you're trying to do is get the model prediction, which is the blue line, to be as close to the black line as possible. Now visually you can see that it's not too bad, right? It tends to miss out on the first part of the rainfall in June, July, I think, but it does catch the October peaks. And this is what you would want your model to do, is that by and large capture the stream flow regime, and if it doesn't, then something is wrong. But now what I want to show you actually is how these react, the flow, how the output reacts to the three parameters that we talked about. So initially, as you saw, these are the outputs, the stream flow output at least, with 40% AWC, a depth of 1000 mm, and a reservoir coefficient of 0.8. Now 0.8 means, like I said, that 80% of the flow is coming out in the same month. So let's see what happens when I change this. Let's make it very less, say just 20%, 0.2. As you can see here, simulated flow is very different now. The peak flows have dropped, the low flows have increased, and they don't match the actual flow record. So let's just move it back to 80%. Now what happens if you change the available water capacity? You can do that in one of two ways. You can change the field capacity here from, say, 40% to 20%. Now this just means that instead of 400 mm being the capacity of the soil to hold water, it's now dropped to 200 mm, and therefore more of the rainfall inputs is becoming stream flow, and so you could see how the stream flow just jumped up. Let's move this back to 40%. Now if you were going to change the depth to, say, just half a meter, same thing would happen, obviously, because the available water content is just a multiplication of the routing depth and the percentage AWC. So as you can see, you have to change AWC and the reservoir coefficient at a minimum, these two, keeping a routing depth constant perhaps. Let's change it back to 1 meter to try and achieve the best fit between actual flow and simulated flow.